Welcome, everybody. So today I'm going to talk about logistic regression. And this is a bit different from standard regression. Hopefully everybody here is somewhat familiar with standard regression. I did a webinar on regression a few weeks ago, or it may have been I guess it was a few weeks ago, right? So if anyone who is listening to this archive hasn't seen that webinar already, you might want to start there. And I'm going to assume a little familiarity with standard regression, but also I'm not going to assume that you're super familiar with logistic regression. Some of you may be coming here to learn what it is. So we'll cover that briefly and see how it's done in Analytica. So everyone is seeing the screen okay, right? I assume you would have told me if you weren't.
Yep.
Okay. Actually, I think I need to do this. There we go. Okay. So let me make a distinction between two types of regression. So in both cases, we're going to start with historical data. So on the screen right now, here's a depiction of one data point. So we observe a bunch of input variables. These are usually called independent variables in statistics. And so x1, x2, up to xm. And we also observe an output variable. It's usually called the dependent variable.
Washington.
Okay, Hank, welcome.
Right.
Okay. So we observe these input variables, we observe this output variable. And that's one data point. And then we observe another observation, so now we have two data points, and so on, and we end up with n data points. And that's our input data set. Now, with standard regression, what we do is we fit a model to that historical data so that we predict the output, y, from those input variables. Okay? Now, with logistic regression, or more generally generalized regression, what we're doing is instead of predicting the output, we're predicting the probability of the output from the inputs. Okay? In general, this might be predicting the probability distribution given the inputs. Now, there is a distinction to be made here. These two things are somewhat different because in the first case, in standard regression, we're predicting exactly what we're observing. But when we're doing logistic regression, what we're going to see is the y's are going to be zeros and ones. Okay, an event occurs, an event doesn't occur. Okay, so an example might be we might collect a bunch of data on a patient. You know, your age, your height, your weight, your cholesterol level, all your blood test results. Okay, and you might collect a bunch of those, and then you might save those for 5 years, and 5 years later look to see if that patient developed diabetes. Okay, and so then you do that with a bunch of patients. You have their data 5 years ago. You have whether they developed diabetes within those 5 years. So the event is 0, 1. They developed diabetes or they didn't. But what we're actually predicting here is the probability that the patient will develop diabetes. So with each data point, we're not observing that probability. We're not given, with these input parameters, there's a 0.7 chance this patient is developing diabetes. See, so that's the distinction. In standard regression, we'd be given 0.7, and we'd be fitting a model to it. In logistic regression, we're not. We're fitting a probability distribution. Now, in linear regression, like we saw in the earlier webinar, this is a picture that sort of depicts a linear regression model. And so what we have here is we have our input variables in the x vector on the very left. And the first step we do is we select a bunch of basis functions. We select these manually that are going to represent the inputs to regression. So sometimes we'll form this basis just using the actual components of the input vector. And we usually add a constant to our basis also, which allows our function to not have to pass through the origin. But in general, we may have the basis be somewhat different from our original independent variables. Sometimes we might add nonlinear terms in there. If we have some reason to believe two variables interact, we might put the product term in there. We might eliminate some of the input variables. There's sometimes good reasons for doing that, and so forth. So from this basis, then, you take each basis term, each of these basis numbers, basis functions is going to be a single number for a single input, and we multiply it by the coefficients, we sum them up, and we have our prediction, right? So that's, hopefully, if everybody has a picture of linear regression and you can kind of map it onto that picture, hopefully it makes sense, okay? Now, in linear regression, then, we run an algorithm that finds the minimum least squares error. So you find the coefficients, C0 through CK, that minimizes the least squared error between your predicted Y for each of your input data points and your observed classification, or your observed output. Okay. Now let's compare this to logistic regression. So one thing that happens here is, remember, in logistic regression, we're trying to predict a probability. That has to be a number between 0 and 1. In this picture, there's nothing that's going to force our value of Y to end up between 0 and 1. Okay? So if you just run a standard regression on data where your outputs are 0 and 1, when you run that on new data points, you're going to get values like negative 0.3 and 1.5 and stuff that don't make sense as probabilities. So the basic idea with logistic regression is we change this picture by taking the output of the sum. Notice the first part looks exactly the same, and we just put it through a linkage function that, notice that the x scale on my drawing goes from 0 to 1. So you take a real valued input from the left, map it through this function, and the output is going to be a number between 0 and 1. So it's going to be able to serve as a probability. Okay? So like I mentioned, in logistic regression, the Y value is considered to be a dichotomous event, meaning it's either true or false. Okay? There's just two outcomes. So this forces your output to be between 0 and 1, and then the actual process of finding the coefficients does it with that linkage function in mind. Okay, so it takes that whole system, the complete output, P of Y, and it finds the coefficients that maximizes the likelihood of the observed data. So if you take a given probability, you take this whole thing, you take an input, you get a probability of the output, you can look, that basically tells you the likelihood of the observed value. Okay, so now the actual techniques here have to be quite a bit different. You can't use the standard regression techniques to do logistic regression. There's various matrix operations that you can do standard regression with. Here you have to do a different kind of search. Okay. Now this linkage function here, really the only thing that matters about that linkage function in the story I just gave is the shape of it. Anything with that basic shape, well, and that such that the output is between 0 and 1, is going to be just fine. And there's a lot of functions that have that shape. Okay, so on this screen here, I have two different functions that have basically that same shape. On the left is what's called the Logit function, and it's z is equal to the log of p over 1 minus p. Okay, you can see the graph, and the inverse of that is shown underneath. Okay, so that's called the Logit function. Another function that has that shape is the inverse cumulative normal, or the inverse CDF of a normal distribution. Okay, actually, really the inverse CDF of any real value distribution has that shape. Okay, the normal is just kind of one choice we could use. So so we could use that as well, and the inverse then is the cum normal, this actual CDF of the normal distribution. So it's not going to make a huge difference which of those two functions we use. They both have the basic shape. They both accomplish the same thing. But the one on the left is the function that people use when they do what's called logistic regression, and the one on the right is what people use when they do what's called probit regression. So these two techniques, you'll often see distinction made in the literature. There's very little distinction between them. They're, for all practical purposes, the same thing. They only differ in a slight twiddle in their underlying mathematical model. There's some historical reasons why some communities out there have used the probit distribution since the beginning of time and continue to do that, and that's the standard in some communities, and in other communities, logistic is the standard. And okay.
So, Lonnie, are you saying that I could use one for the other and get the same accuracy in the answers?
No, you'll end up getting different results. It's hard to predict which one's going to do better a priori. I mean, unless there's some other knowledge you could bring to bear, but I'm not even sure how I would ever bring other knowledge to bear to make that choice. So, but if you actually run them on data sets, you'll find that little difference does make a difference.
Okay.
You know, so if you compare them, you'll find you do get different results. Sometimes one will work better than the other.
So you could find out which has the best likelihood with a Kaiki information criterion, couldn't you?
Yeah. So in this case, I don't think the Kaiki information criteria is going to give you any real information, because what that really does is it accounts for the number of parameters that are going into the function. And in fact, both of these have the same number of parameters going in. And so actually, if you just simply look at the likelihood of these two, you know, you'll get the same thing out that you would if you looked at an Kaiki information criteria. Okay. Now, if you were comparing a set of possible functions that had more degrees of freedom, so you were comparing a function that had 1 degree of freedom to one that had 2 degrees of freedom, you know, here, that's where the Kaiki criteria would help you compare them, because the one with 2 degrees of freedom is almost certain to always get a better fit, but sometimes it might be overfitting because it has more parameters. Does that make sense?
Yep.
Yeah.
Okay. So I will say, though, that if you do, well, okay, there's some overfitting things here. You know, if you do actually compare the two and take the one that's best, you have actually added an extra degree of freedom to your analysis, which may hurt or help. So anyway, there's a lot of issues with overfitting that come into play here. All right, so I'm switching over to Analytica now. And as a starting point here, I have brought in a data set that we can play with. So what I have here is, here are the independent variables that we're going to use, and here is the dependent variable. And so this data set is a breast cancer data set where some tissue samples were taken from patients, and each of the rows corresponds to one tissue sample, presumably one patient. And from those tissue samples, a whole bunch of measurements were taken, and that's what the columns represent in the independent variables here. So there's quite a few of these in here, but a bunch of these measurements were taken, and then for each tissue sample, it was determined whether that tissue sample was a benign or a malignant tumor. And so if it was malignant, the dependent value is 1. And this is a standard data set from the UCI machine learning repository. So people use this in the machine learning community to test various algorithms. So we'll use this as a starting point. Now, what we're going to start with is coming up with a basis that we're going to do our regression off of. And what I'm going to do here is I'm just going to use the features that are here as my basis, except that I'm going to add in a 1. Because usually when you do regression, you want that constant term in your basis so that you can have an offset. Otherwise, you're forcing everything to pass through the origin, which is not always appropriate. So I'll use an index called k to represent the basis. So I'll just concat a 1 onto the front of this feature vector, and that will be my basis index. And then for the basis itself, I just want to concatenate a 1 on the top and reindex. So I'm going to actually, well, here, I'm going to need to have a temporary index here. You'll see why. So I'm going to take the value 1. I want to concatenate that onto data. And now the next two parameters are the index of the first parameter And for that, I really just want an index that has one element. And I don't have that index yet, so I'm just going to go like this. Okay. And then I have my original index, and then lastly I need the result index, which is k. So what I've done now is I've just re-indexed data, the original set of, let me pivot, the original set of independent variables, and I've just added this column 1 in front. Okay? And that gives us our basis, good starting point for regression. Now the other thing I'm going to do before we get into this too far is I'm going to split my data into two sets, because we could use all the data to do the fit, to compute the coefficients and everything, and we could see how we did on that same data. But really that's not very informative, because when you do a regression like this, or a logistic regression, you're usually more interested in how you're doing on new patients that you haven't seen yet. So I'm going to use these patients to obtain a model, but then presumably I'm going to use this model in the future on patients I haven't seen yet. And so by dividing the data into two sets, we can train on one of those sets, and then we can see how we're doing using the data from the other set. Okay? So what I'll do here is I will say train ID is going to be a subset of the IDs up above. So we could actually, before I do this definition, we could decide how many many patients should go into the training set. So I'll say percent used for training. Okay, so let's say 70% of them will be used for training, 30% for testing. Okay, so what I can do here is I can say if the position of ID is less than percent used for training times the size of ID, then I'll keep it. Okay, and so that would keep the first 70% of the patients. To make this a little bit more interesting too, we could randomly pick 70%. We could pick it wouldn't have to be necessarily the first 70%. So I could do that this way. I could say shuffle the IDs and then re-index. Okay? So if I do that here, we get these. I'm going to actually format this as an integer because my patient IDs are integers. Okay? And we have a subset of the original data, not necessarily in the same order because I randomly shuffled. Okay? And then we can also use a test index. So all of the points that aren't in the training data I'm going to use in the test data. So what I could do here is I could say, this syntax here would say, okay, that's what is the position of the original ID in my training ID, okay? And if it's not there, it's going to say 0. Okay, so the ones that aren't there, okay, are the ones that aren't appearing in training ID. So I'm just going to keep that subset. Okay, so test ID is the set of IDs that are not in the training set. Okay, so here's the other subset of things. So I'll go ahead and format that as an integer. Okay, so there's the patient's, the other subset. Okay, real quick as a sanity check, I'm going to go into TypeScript. Okay, Control apostrophe, and we can see the original ID had 569. The train ID has about 400, and the test ID has 171. So that looks like that looks right. Okay. So given that, let's go ahead and compare logistic and linear to each other. So we'll start with linear regression. Linear regression C. We're going to compute these coefficients. Okay. So we'll use the regression function to do this. The classification is malignant, but of course we want to use only the training data points. The basis, again, we want to use only the training data points. Okay. The data index is the training ID, and the basis index is K. All right. So this is from regression like we saw before. If I evaluate that, there's our regression coefficients. Okay. Now, we'll go ahead and do the logistic regression coefficients. Logistic C. All right. To use logistic regression, we need to add in a library that gives us this function. So before I define this function, I'm going to go ahead and do add library. And I'm going to select the generalized regression library. Okay. I'll embed it. Okay. And inside this library, you'll see there is a logistic regression function, a probit regression function, Poisson. We'll see this stuff a little bit later. And here is that Logit function we talked about earlier and the inverse Logit. Okay? So, what we're going to do here is I'm just going to, first of all, I'm going to copy paste the same definition we used when we did the regression function. Okay? You guys might be somewhat familiar with regression. So, logistic regression, conveniently enough, is exactly the same. We just changed the name of the function to logistic regression. Same exact parameters as regression. And now we can go ahead and compute that. And, oh, man. Okay, this is, I'm going to do something real quick here, if you don't mind. That message that just came up is a real annoyance, and it occurs because I happen to launch Analytica from my debugging environment, and the optimizer gives this message when I do that. So let me just quit this for a second and restart Analytica outside of the debugger so it doesn't give those messages. Hold on with me for a minute. I guess I'll just use this one. Okay. I like to use my most recent build that I'm working on so that using a current build when doing demos is got to be the most foolproof way of finding bugs. So I don't like bugs to get through the development process. So, but I'll go back to the 3.1 release here. Okay, so we've computed. Well, I'll recompute. We've computed these coefficients now for the logistic regression. Now, at this point, one thing that's kind of interesting is to actually compare these coefficients. So we have the ones that were computed by the logistic regression. We have the ones that were computed by the linear regression. And it's kind of interesting to compare them. Now, they're not on the same scale. Okay, so you don't want to compare absolute values when you look at these because we've squashed the logistic case, the sum and stuff, when we went through that function, and it could completely distort the scale of these coefficient numbers. But the relative magnitudes can be quite interesting. So just looking at this, I can see, well, actually, it's kind of hard to just look at it numerically. I mean, I see some of these seem to be much bigger, like a factor of 300 between one and the other. But a nice way to compare this would be to do a scatter plot. And so when we do a scatter plot here, I'll compare logistic to linear, C, and graph it as a scatter plot. Okay, and one thing that what can become interesting here is that the sometimes you'll see that there will be coefficients in the logistic case that are really big when the coefficient in the linear case is very close to 0. And I can see I have my fonts set sort of weird. I was screwing around with some some things on this model before the talk. Actually, you know what? I wanted to set default on that. Let me let's see. We'll just make it. I think I've changed it here. Okay, good enough. So so this point right here, for example, this is the smoothness worst. This point is pretty close to 0 in the logistic case. So logistic is not putting much emphasis on that point. But in the linear case, you can see it's put a lot of weight. It actually has the most weight in the linear case. So the two different regressions sometimes rate the features very differently. Okay. Now, what are the actual predictions being made by these? So in the linear case, what we can do is, okay, so linear regression. Here's the probability of y, the probability of the predicted. Let me see here. I think it might be useful also just to put the test value of y here as a separate variable. So here we're going to take malignant is actually our y value. I failed to mention earlier, by the way, that I actually gave malignant the identifier y. So you may have wondered where y came from. I didn't realize I didn't mention that. So our test value for y here is going to be the reindexed value, where we're using just the test samples. Okay, so I'm going to just pull out the subset of test samples. I think that will be convenient for a couple things. Okay, so how do we actually find out what our predictions are on the test set using these linear coefficients? Well, we take the linear coefficients times the basis terms. So here we need to take just the basis terms for the test set, and then we sum over our basis index. Okay, so hopefully you can remember this from the regression webinar. And so we can look at these predictions now from the linear regression. And, well, right off the bat, you can see weirdness, right? Because this is supposed to be a probability, and it's coming out with 1.3. But we knew that was going to happen with straight linear regression, right? Down here we get a negative number. So those aren't meaningful probabilities. But we might actually now compare this to the test y that I just created. Okay. So put them side by side. See, well, at least when it predicted 1.3, the true value, in fact, was 1. And up here you can see these look like pretty high probability numbers. Well, most of them. And we're getting 1s. Here we got 0.3, but, you know, it should happen 30% of the time. So down here the numbers are smaller, and we're getting 0s. So there's certainly, I mean, visually you can see there's a pretty obvious relationship of some sort between the actual values and what's being predicted. And we might even graph this as a scatter plot. And here you can see that relationship. So the true value is on the x-axis, and the true value is either a 0 or a 1. And the actual predicted value, predicted probability, is on the y-axis. And so you can see there's, you know, a correlation. Over here in the low range, well, when the test y is down below about 0.2, it seems to be getting everything right, right? And when it's up here above about 0.8, it seems to be getting everything right. And then there's a big gray area in between where it's kind of overlapping. Okay, hope that makes sense. All right, but we should do something about these weird numbers. So let's just make a slight adjustment here, just a total hack. I'll just say, let's say if p is less than 0, then let's use 0. Else, if p is greater than 1, then use 1. Otherwise, we'll use p. So we just kind of can threshold that and get a little bit nicer probability out of it. So we're ending at 0, 1. Okay. All right. How do we predict the probability for the logistic regression? Well, kind of the same idea. I'll start by doing what we did before, where I take the coefficients times the basis for the training points, summed over the basis index. But then what we need to do is we need to pass this through that logistic function, remember? And actually we're passing it through backwards. We're going in on the y-axis and coming out the x-axis. Remember my drawing? So we're actually going to use the inverse Logit function. Okay? So this gives us our probabilities here. All right? So some of those numbers are really close to 1s and 0s. And was more than usual, but that often happens. If you get out very far on that logistic function, you very quickly come out to where you're so close to 1 or 0 that, you know, with 4 digits of numeric precision, it looks like a 1 or a 0. So we can go ahead and compare this also to our test result and kind of see how it's doing. And that one right there looks really odd. I don't usually see that happening. makes me think I've done something wrong here. So you can see here it's predicting a very small probability. Well, this is on a test data point though that we haven't trained on, so that's not impossible. But but yeah, I usually don't see them quite so bad. It makes me think I've made a mistake here. I don't know. Just to give me a sanity check, I'm going to reshuffle and redo this and see if it changes at all. So, okay. Well, I'll continue here. Those numbers, some of those are taking me by surprise. So, I often do see logistic regression though when I've used it. A common problem is you'll see it seems like it gets a little too confident. I've seen linear regression do even worse when we do what we've just done, but this is kind of a manifestation of overfitting. This is the standard problem we have in all data fitting applications. Okay, we can go ahead and plot this as a scatter plot as well. Oh, I've already added that, so and get this picture. Sometimes I like to swap x, y here and look at it this way, so we can kind of see the point. So up here you can see that here's a case where we're predicting a very small probability, but the actual result is true. So that's a really bad prediction. We can imagine that happening occasionally, but okay. Anyway, now we could talk about scoring these. Okay, we could look at how good we're doing a number of ways, actually. So one way to do that is to look at the log likelihood score. And the reason I say log is because the likelihood numbers get so small that they'll tend to underflow numeric precision. So what we do here, though, is basically if we've predicted a 0.8 and the true value is a 1, the 0.8 tells us really the likelihood of the data for that data point. If we've predicted a 0.8 and the true value is a 0, then we'd say the likelihood of that 0 was a 0.2 given our model. So if you take all those likelihoods and you multiply them all together, you get the likelihood of the entire data set, which usually comes out to be a really small number. So we take the log likelihood and it's a reasonable number. So that's the L score. Now, if you attended a webinar I gave on probability assessment, we talked about scoring techniques and how they can be used to really measure the quality of an assessment. The same type ideas apply here as well. The scoring techniques can be used to measure the quality of a fit like this. Okay, so here's our prediction. I'll just call it P. It's going to be an array that's indexed by, oops, if I can hit the right key, by test ID. And so what we can do is we can say if the real value is true, then P is our likelihood. Otherwise, 1 minus P is our likelihood. Okay. And then we want to sum the logs of those. Let me do it the other way. Sum the logs of those over the test points. And that'll give us our log likelihood score. So we could look at the score of each of these. So I'm going to do one more thing here. I have an index in here that I'm going to borrow for a minute. The data fit model, I'll make an alias of it, and I will drag it over to our diagram so we can look at that. Okay, so this is a choice where I have logistic, probit, and linear on it. And so what I can do here is I can just kind of combine these here into a single variable, so I don't have to do everything separately. And I'll make a determ table off of this index. And we have logistic, the probit we haven't done yet, and the linear. And so so here I can select which model I want to look at or select all. So here we have a comparison of the actual probabilities. Okay, so actually if I pivot it. So here's a comparison of how each of the two models did next to each other. And then now I can actually look at the score for each of these. Okay, so we haven't done the probit model yet, but you can see in this case, actually, the higher the number, the better the score. So even though some of those points I pointed out looked like they weren't too good, Logistic is actually outperforming linear substantially. And remember now, these numbers are the log likelihood of the data. We've taken the log. So what it's saying is the probability of seeing this test data, if our model's correct, would be e raised to the negative 19 or e raised to the negative 34. So the difference there is that the likelihood of Logistic is something like e to the 14 better than linear. That's a big number, right? E to the 14 it's a million times better. Okay, so you're getting a likelihood. Okay, so in fact, the Logistic is, by that scoring, doing quite a bit better. We can also look at some other graphs here of how well it's doing. So one interesting way to look at this is to, first of all, look at the, well, here, I'm going to show you how to a neat comparison here. So I'm going to take the data points, and I'm going to rank them according to the sum of the probability plus the true classification. And this is going to give me an ordering on the points where the predictions that are closer to 0 are going to be on the left, and the ones that are closer to 1 are on the right, which will make for a nice graph. I'll show you that in a second. And so we're going to rank those along the test ID. And then what we can do is compare actual with P. And so here I'm going to just take the prediction and the actual classification, and I'm going to use some graphing magic here to come up with a cool graph. So I'm going to use our ID rank that I just created as one of the comparison variables. And what I want to do is I want to use that ID rank on the horizontal axis. I want to use our comparison as both the common index and the key. I want to, hold on a second, okay. I want to use a line graph, and my data rank must not be right. Hold on a second. I have our, that looks okay. Okay, hold on. Let's see if what else do I have here? I'm just looking around a little bit here. Hold on. Bear with me. We have test ID. I should have data fit model coming through here, although common index is data fit model. Here we go. Horizontal axis is ID rank. Key, I want compare. I think. Hold on a second. Hold on. How do I do this? Oh, I know. I think I need to put separate keys on here, and then it will let me do it. Okay, so we're going to have the common index be the test ID. The horizontal axis will be the rank. And for the symbol key, I want compare. And for the common index, I want compare. There's the graph I want. Okay. Took me a little while. And test ID shouldn't be up there. How come it's up there? Test ID is up there. Does that have an all option on it? Well, it's coming out to be the graph I want, so I'll worry about it later. So this graph is kind of neat because what it's doing is it's putting the predicted probability on there. It's putting the actual classification, which is a 0, 1, on there, and it's connecting the predicted probability with the actual classification. Okay. So the way I did that was I created this comparison where I have the probability and the actual, test Y and P of Y, and I use that as the common index. So it means it connects a line between P of Y and test of Y. Okay. I reordered the data points by their rank so that they would come out in kind of an increasing fashion like that. So so we can see the lower predictions on the left and the greater ones on the right. Okay, so that gives you kind of a neat picture of how Logistic did. And if we looked at linear, we have another depiction here. And I guess what you're seeing here is that really Logistic can predict a lot of the data points that we're seeing with a lot of confidence. So there's just a very small gray area in there where it's having trouble predicting them and has to give an actual probability, while the linear case is sort of across the board. Okay, it's sort of across the board. It's gray area. All right. So.
Could you say again how you got ID rank, the horizontal axis?
Yeah, that was ordering the data points. Okay, so actually look at the graph for a second. It might be a little clearer. So what I wanted to do here is I have two things going on here. I have the actual value 1, 0, and I have the probability of the prediction. And so basically, I wanted to sort the data points, the patients, so that if the true prediction was a 0, I wanted it to be to the left of if any of them where the true prediction was a 1. Okay, so you can think of the true prediction being my first sort key, primary sort key. Okay, so everything has a true value of 0, observed value of 0, is to the left of everything has an observed value of 1. And then as a secondary sort key, I want to use the probability. So those, are basically increasing. So actually, if I just add the probability to the actual value, that does that for me, because the probabilities are always between 0 and 1, right? And so if the true value is 1, you'll have a value bigger than 1. If it's 0, you'll have a value between 0 and 1. So I added those together to sort of come up with a dual sort key, and then I used the rank. So the rank just is kind of the inverse of sort. It just tells you for each data point, it's the first point, the second point, the third point. And then the graphing engine itself takes that. Graphing engine itself takes that and puts it in the appropriate place on the x-axis. Okay. So, all right. So let's add probit regression into this mix, and so we can kind of compare it. And it's obviously basically exactly the same thing we did here. I'll just copy this and use the probit function. And I'll again just probit P of Y. All right, so here again we're going to use, let me just copy this and then make the change. So we want to use the coefficients that we got from probit, of course, and we don't use the logistic function, we use the cum normal function. Okay, because remember the probit is the inverse CDF of the normal, and we're going through the y-axis, so we actually use the cum normal function. Okay, and so see if that gives us some coefficients and some predicted probabilities. Looks like it's thinking a little bit here. There we go. Okay, and let's go ahead and add that into our mix here. So, okay. So we can first of all, we could compare the scores. So here's our scores, and Logistic's doing a little bit better than probit is in this case, but probit's doing better than linear. Okay, and we could look at the predictions here. So here's Logistic, there's probit. So interestingly, the gray area has shifted a little, I think. Yeah. So, okay. We could actually use color to look at them at the same time, I think. Actual C. I'm not sure why we're getting test ID on this graph. I don't think I should be getting test ID. Makes me think I did something wrong. Color, symbol, horizontal is ID rank. So I don't know why that's not coming out to be the graph I expected. I messed something up here, huh? Compare, ID rank, linear. I don't know why this guy's coming up here. I don't get it. Well, there we go. Okay, so does that do it for me? That does it for me. There we go. Okay, so okay, so here now we are seeing the we're seeing all of these on top of each other. If you can make any sense of that, but actually, with them on top of each other, the x-axis hasn't been rescaled. It looks like there actually is, the gray area is approximately in the same location for Probit and Logistic. If you can see that. Okay. So anyway, Probit and Logistic, like I say, are extremely similar. Now, another way we can look at this is to histogram the actual error. So the error in the prediction is the difference between P of y and the 1 or 0 that came out. So we could say the histogram of the error. So PDF is a function in Analytica that will make histograms for you. And so we could histogram the difference between the probability and the actual value. And we want to histogram those over the test data ID. And so here, let's graph it and use a comparison index. So, okay, so let's see here if we can make this look like what we want. Okay, and now I just want to make it a step graph. Okay, so there's a histogram of the errors, and it looks like both the Logit and Probit have very similar-looking histograms of error, and you can see that the linear has quite a few more errors that are greater than 0.05. Okay, so there's some interesting ways of looking at it. Okay, now let's see. Inside the regression library, I'm going to go on to just show you a little tour of this guy. As I mentioned, we have these functions, logistic and probit regression, that we've just utilized, and the Logit functions. And there's an example in here as well, which I'll just bring up and show. So here we have some example data, and similar to what we had before, here we have just 3 independent variables. Okay, and for each of those independent variables, we have a 0-1 classification. I hope I'm not going too fast for GoToMeeting here. And then what we've done is we've created a basis. So right here, I've just selected out the first component of the data. Okay, so the first column of the data, second column. But then in assembling the basis here, you can see that we've assembled a basis where we've used the constant term again. We've used the original independent variables, and then we used product combinations of those. So if there's interactions between the variables, we can potentially catch them with those terms there.
Just as a reminder, on the first set, the previous set, the breast cancer data, you just used all the available independent variables as the basis?
Exactly. And I added in a 1. That was the only modification I made.
Okay, great.
So that was the equivalent of using just those. So here you see we've brought in additional terms into the basis beyond what is in the original data. So we can potentially capture interactive terms, interactions. And again, we have this data fit model here where we can look at any of the 3 models. And I've actually created the same graphs in this example that I just showed you how to create there. So you can look at this library also to see an example of those. So for the histogram of the errors here, we can see how it does. It's this one. The results actually look a little bit different here. The logistic and probit. Well, it looks like logistic is clearly doing the best, right? It's most of its errors are small, while the probit is stretched out a little bit more, and the linear, interestingly, has very few good classifications, and almost all of them are out here in the larger space. Now, this particular example does not divide the data into training and test data. It actually is just measuring the performance on the same data. So, you know, it's fit the model to the data, and then it's looking at how it did on those original data points.
Can you remind me what you used for the x-axis here, it's the error. It's just calculated as the probability calculation versus 0 or 1.
Yes, exactly. So it's the absolute difference between the probability and 0 or 1. Exactly.
From probability to what it really was.
Yes.
Great.
Okay. So, okay. The here's the neat-looking graph again. It doesn't quite fit on this window. Let's see if I can grab the corner there and resize it. Okay. So here's that graph for logistic. Here it is for probit. Here it is for linear. So again, in this case, it looks like for linear, every data point looks like gray area, right? For the logistic, there's kind of a region down here and a region of points over here where the classification is nearly certain. It's putting out a very confident prediction. And then this area in the middle here is the gray area. It's a little bit wider than in the breast cancer data set. And probit is kind of similar. Okay. So those are some additional examples you can look at.
As far as the interaction terms in the basis, anything to say about those? Or?
Yeah, let's look at the actual coefficients here. So in this data set, we could just look at the actual absolute values of the coefficients compared to the other ones. So so the interaction term here is certainly on par with some of the other terms up here. So it is actually utilizing those interaction terms.
Does the value of the coefficient depend on the scale of the independent variable?
Yeah, that's a good question. Yeah, that's a good point. They do, right? So if these values are pretty uniform between 0 and 1, or -1 and 1, it looks like. So so actually, that would really cause one of these coefficients to naturally become bigger, wouldn't it? So so you're right. Actually, comparing, I guess you probably need to compare the square root of one of these coefficients to the square of one of these. That would sort of give you a better comparison in this case, I guess.
Or just some what's the coefficient statistic called? Is it the t-statistic? It's the coefficient divided by the standard deviation of the estimated standard deviation. Yeah,
that's the z coefficient. But yeah, and then but you're right. I think actually that would be the most legitimate way to do it. Is I think there probably would be a statistical test like that would look at the a significance level. So okay, so I'm hand waving right here on this, but okay, we can see that difference. Those are good points actually, and a lot of times people do regression and logistic regression not just to be able to predict the outcome on new data points, but also to actually look at the coefficients themselves as a sensitivity measure. You know, saying this coefficient really is telling me how much this term contributes to the result. So it's a pretty legitimate sensitivity measure. So so those comments are really relevant. Now, Poisson regression. Let me say a few words about Poisson regression. Remember, logistic regression and probit regression are really the same technique. They deal with the case where you're predicting the probability of an event. Poisson regression is in that same category of generalized regression, but here the difference is the output variable is a count, an integer count. So instead of being that an event occurred or an event did not occur, it's how many times did an event occur. So our observed y's are going to be integer numbers, counting those, and the actual result of a Poisson regression is going to be a Poisson distribution over the integers, over the positive integers. Okay, and so here I'm just going to draw on the example that's in here. So here we have example data again. Actually, it's looks like the same independent variables, but our dependent variable here are these counts, 8, 8, 10, 17, and so forth. And so what we do with a Poisson distribution, with a Poisson regression, is, again, the function is exactly the same as all the other regression functions we've seen, exactly the same parameters. And when you evaluate it, you get a vector of coefficients, the same way you did with the other ones. But what we can do with those coefficients is come up with the actual mean value for the distribution. And here, the linkage function is the exponential function. And so here, instead of using the inverse logit, well, it's actually the log function. So the inverse of log is exponential. So where we used inverse logit before, we're going to use the exponential function here. And what that gives us is the mean value for the Poisson. And am I comparing to something? Okay, well, I'm sorry. Well, no, that's right. That's right. Okay, so what that's saying is that now for each data point, you put your independent variables in there, and it's going to give you a mean value out, which gives you the Poisson distribution, because that is the parameter to a Poisson distribution. Okay, so that mean value says use a Poisson distribution with that mean, and that's your distribution over the predicted counts. And so here we have compared the actual prediction to the true count. And so here the mean Poisson prediction is 8.009, and the actual value is 8. Okay, so here the mean prediction is 11.53. Remember now, that's really characterizing the entire Poisson distribution. That's just the mean, where the true value is 13. Okay, so here's one where it's a little bit more dramatically different. Okay, and so here we have the, let's see. So here's the actual distributions, it looks like. I assume we're going to have an index on here. Yeah, we have so many things plotted on top of each other, the graph looks black. So what we want to do here is look at one instance at a time. Actually, I'm not quite sure why I would have set up a graph to compare the two on this scale. So let me take the grid off. So, well, I don't know. That's really, we can look at one point at a time, the Poisson distribution, one point at a time. But I guess that's not a very meaningful thing there. So here's what's this? The average difference between the mean and the actual. Okay, so here's the average. Here's the distribution of error. And I haven't taken the absolute value, so you can see how closely the mean is tracking the actual prediction. So anyway, histogram of likelihoods, histogram of error. Okay, so I guess we're at 11 here. So the Poisson, again, the Poisson fits into that second category of regression techniques, where what we're really doing is pulling out a distribution, but instead of being on a 0-1 variable, it's on a count. You know, integer valued variable. So those are available. Now, the abstract for this mentioned that these functions all require the optimizer, and that's because, as I said, you have to use different techniques to do logistic regression, and in fact, you do an optimization search for those. But these functions, you can all look at the actual definition for these functions, how they're written, and you'll find that all three of the regression functions look almost the same and really just differ in the objective function. And what's neat here is, okay, the logistic function here uses a logit likelihood function, okay, which you can look at also in this model. And what's neat here is you can do other forms of generalized regression just by replacing that objective function. So if you wanted to put a Cox model in, or I think certain types of discriminant analysis are in this category, and so forth, it's really easy to modify these functions to do that. Now,
Lonnie, are you familiar with the Johnson distributions, SU, SB?
I'm not.
Okay, Johnson and Colts wrote a book on distribution theory, and what he does is almost the same thing. He does a functional mapping to convert it into a classical distribution. and it's almost the identical thing. He wrote the 4-volume set on distributions and statistical decisions.
Do you have a title for that?
Yeah, Johnson and Colts.
Oh, that's the author.
And they have a 4-volume set on probability distributions, and in that he mentions his papers and shows some of it. Basically, he's got a classic distribution that supposedly fits everything. Sort of like, the Pearson distributions. It's a takeoff on that.
Okay.
But it's almost identical to what you're doing. He uses a function and fits the function to it. And then some of his questions of, which one fits the best is probably an extension of this.
Good. Nice reference. Excellent. Thank you. So I'll mention, too, if you want to put in your own functions here, the ones that are in Analytica here have included the gradient and Hessian of the log likelihood function. That just helps speed up the optimizer, but it's not absolutely essential. So you don't necessarily have to put those in there. And, in fact, the engines that come with the standard optimizer don't use the Hessian. They only use the gradient. So those are just optional. There are some add-on engines you can get, like Nitro, that will make use of the Hessian. But okay. So anyway, the point is here, you can just copy these if you want to use other parametric forms of generalized regression. Okay. So that's it. I hope everybody who didn't know what logistic regression was now have some idea, and those who did, and hopefully have gotten some idea how to actually do this kind of analysis in Analytica. And
can I ask you have something else to say? Sorry.
Go ahead and ask it.
I noticed in the manual regression using a potpourri of terms. Or no, that was in the examples. It was in some of the example models, I think.
Yeah. Okay. Actually. Okay. Go ahead.
You know what that is?
Yeah. So here's a situation that you come up with in regression, which is you have some data, perhaps a whole bunch of independent variables, and you have all sorts of potential interactive terms and nonlinear terms and all sorts of things like that potentially could be useful. And you don't know which of those are going to be predictive of your data. So you could theoretically throw everything you can think of at it and have this really large basis, right? Really large number of basis functions. Now, in regression, in standard regression, when you do that, what you'll find is, because standard regression relies on matrix manipulations, if you take a simple regression algorithm, most of them will have a lot of problems because there will be redundancy in those terms. They won't be totally linearly separable, and that will cause singularities in the algorithms that will cause most regression functions to fail. Okay, so if you had the same variable in there twice, or the same basis function in there twice, there's not a unique solution, right? You could actually adjust the coefficients, as long as the sum of them is the same. You could take any combination, and the function in Analytica regression is very robust to that. So it doesn't get confused if you have redundant terms in your basis. It actually does a good job at picking. Say it again.
Does it use a pseudo-inverse, basically?
Yeah. It's based on singular value decomposition. So, but yeah, you can think of it as being like a pseudo-inverse that's robust to that. So that's what that refers to. Now, when you're doing the logistic regression, it's using a search. It should be fairly robust to that as well, because it will just find one of those points. So there may be a lot of equivalent coefficient vectors that really, are identical in their prediction given that basis, but are radically different in the coefficients because the coefficients are not linearly separable. And so it doesn't really matter. It's just going to find one of those when you do the the search. So now it might matter if you're actually looking at
does the search, or I mean by search you mean searching for the best,
the maximum likelihood.
Variables.
Yeah. So it's going to come up with one of those that happens to maximize likelihood. You know, with not making any distinction between them really. So, you might want to be aware of that a little bit if you're actually looking at the coefficients themselves, you know, as a sensitivity measure. Be aware that if there are, you know, if one of the coefficients is a linear combination of the other ones, or sorry, one of the basis terms is a linear combination of the other ones, then your coefficients can lose meaningfulness. You know, but as long as you keep that in mind, you know, you still will get a coefficient vector out that maximizes likelihood. So, okay. Good. Are there other questions?
Could somebody repeat that reference to Johnson and Coates?
Yeah.
How do you spell Coates?
K-O-L-T-Z.
I just looked it up as K-O-T-Z, or at least
K-O-T-Z.
I just did a, yeah. If you do probability, you just do a Google search, probability distribution Johnson, then I came up with Coates.
Yeah, there's a 4-volume set on distributions that he wrote a while ago.
Okay, thanks.
Right.
All right. Thank you, everybody.
Thanks, Lonnie.
Okay.
Yeah, it makes things very clear. Very lucid presentation, Lonnie.
Well, thank you. I struggled a little bit on how to present this clearly, so I'm glad that.
There's a lot of people who tried and failed.
Great, thanks a lot.
Okay.
Right.
Thank you.
It sure shows the power of